Speaker in this session is Lea Friedli from Technical University of Munich, and she's going to speak about scoring Gaussian process predictions for sequential design of experiments. Please start when you are ready.
Okay, thanks a lot. So hello everyone. So my name is Lea Friedli, and currently I'm a postdoc at the Technical University of Munich. But the work I'm talking about today was started and also mainly done while I was still a postdoc at the University of Bern with David Ginsburger as my advisor. Also, the work I'm talking about today wasn't done just by me. I had a lot of very good co-authors, which you can see on this list on the first slide. So today I will be talking about scoring Gaussian process predictions for sequential design of experiments, and I'm doing this in the context of two applications. It's about molecule and plant selection, and the plant selection applications comes from the domain of agriculture, where it's very common that you have to select specific plants or varieties of a plant given specific environmental conditions. This is very important because it ensures reliable food production and also stable incomes for the growers. So different varieties of a certain plant can handle different environmental conditions, and this becomes even more important in the face of climate change. The application in chemistry is facing another challenge, and it's one where we are actually interested in certain molecules. So we want to identify and describe molecules which have specific properties. That can be very critical, for instance, in medication development, where you are looking, let's say, for a molecule which has a solubility in water, which is lying in a specific range. Both of those applications have some things in common. One thing is that you have a huge number of potential input points, which can lead to your desirable outcome. As there is a lot of input points, you cannot test all of them, and it makes a lot of sense to use a surrogate model to prioritize promising candidates which you actually want to test. What we are doing is that as the surrogate model, we are using a GP model, which was already talked about this morning. So very briefly, a GP model has the aim to model a function f, which goes from an input space to the real numbers in the most well-known form. And we do that based on a finite number of pointwise evaluations. So quickly back to the applications. In the chemistry application, we want to model how a molecule maps to the property of interest. In agriculture, we want to know how a variety environment combination maps to the performance input we're interested in. What we are doing now in GP modeling is that we assume that this function f is a realization of a Gaussian process with a mean function and a covariance kernel. So, however we are choosing this covariance kernel, it has to be able to handle the input space. And then using this potentially noisy or not noisy observational event, we are conditioning the Gaussian process on the observation event, and we are getting a posterior Gaussian process with the mean and the covariance kernel given by the very well-known Kriging equations. In the main part of this talk, I will be talking about the chemistry example, and that's also why I'm now quickly taking this GP modeling framework, taking it to chemistry. So in molecular spaces, as I already said, our inputs are molecules. Molecules can be huge, they're three-dimensional, and they can have very complex structures. So before we can select a kernel for a molecular space, we have to consider what kind of representation for the molecule we are using. We are relying here on fingerprints, which are just binary sequences which encode the presence and absence of certain substructures in the molecule. Using these binary substructures, we are then using the Tanimoto kernel. We're not the first ones to do that, that has been done quite a lot. And the basic idea is here of the Tanimoto kernel that it counts the number of common present features of two molecules, and it normalizes this common number by the total number of features present. I'm not going to focus generally on any kind of kernel choices today. It's not the main topic of the talk, but of course there are many other possibilities and many other options. The dataset I'm going to use today is the photo switch dataset, which includes photo-switch molecules. Photo-switch molecules are molecules which can undergo a reversible transformation when exposed to light. That means the setting we are considering is one where we have as an input the molecule represented by this fingerprint, and as an output we have the transition wavelength under which this molecule is doing this reversible transformation. The photoswitch dataset has about 400 molecules, and if we are training a first Gaussian process on this dataset, it can look like follows. So here we are using 100 training molecules. We're assuming the observations to be noisy. So in red, as red crosses, you can see the noisy observed transition wavelengths of these 100 molecules. And then we are conditioning a GP on those observations. And for the remaining about 300 molecules, we get the predictions indicated with these light blue bars, where we are using the predictive mean plus minus 1 standard deviation. As I already said, generally we are interested in molecules with specific properties. In this talk, I'm focusing on molecules which have a property which is greater or equal than T, giving us the excursion set of F above T. So that means that we are interested in having good predictions of our GP in this region where the response is greater or equal than T. But what does that mean? When is a prediction of a GP good with respect to an excursion set? So first, if we are just for the moment saying we are considering the molecule number 259. If we are just considering one molecule, our prediction is just going to be a Gaussian given by the predictive mean and the predictive variance. Now we have a true value in that point, which we all know can now be evaluated using scoring rules. There's going to be a talk about this tomorrow. We already heard the announcement. So one very well-known scoring rule is the continuous ranked probability score, which is defined like this. So it's just the integral of the squared distance between the CDF and an indicator function of the observation. That's a very nice tool we can use, so that's useful to now evaluate the GP, but I also said that we are actually now interested in this excursion set lambda. So to now put some more focus on the excursion set, what we are using is a weighted version of this scoring rule, which is not our invention, has been invented by someone else, but there is one version which we are using, which is the threshold weighted CRPS, which is just given by exactly the same formula as the CRPS, but now we are integrating with respect to a weighting measure. Given that we're interested in the excursion set, we can now cleverly select our weighting measure, and the two we are considering at the moment is one which relies on an indicator function given by the threshold T. So in this version, it's the figure in the middle. You can see that we're basically only considering the differences between CDF and indicator in the region above T, so in the excursion set. And in the second one, we're using a weighting measure, which is a Gaussian around the threshold T, meaning that the distances between the CDF and the indicator are weighted differently depending on how close to the threshold we are. Wonderful. So far, so good. So what we did now is scoring Gaussian process predictions with respect to the excursion set. I hope you agree with me about that. But as you maybe remember, the title of my talk was Scoring Gaussian Process Predictions for Sequential Design of Experiments, so that's where we have to go. The basic idea of sequential design of experiment is that at the moment we're training with 100 molecules. But we now have our groups of chemists, of friend chemists, who are asking us, yeah, which molecules should we test next? What makes sense? And we want to give them some very good tips which molecules they should test. And we generally do that by selecting the next molecule or the next molecules such that they ideally reduce the future uncertainty of the GP, especially in proximity to this excursion set lambda. So, as we said, we now have an evaluation measure of the GP with respect to lambda. It would be very tempting to just say, okay, as the next molecule, of course, we're going to test the molecule which has currently the highest threshold-weighted CRPS. Of course, that doesn't work because the threshold-weighted CRPS is relying on the actual response of our molecule. If we would have all these actual responses, the whole thing wouldn't make a lot of sense. So what we have to do is that we have to find a way around this, and for that reason, we're not using the threshold-weighted CRPS, but we are using an expected version of the threshold-weighted CRPS, where we integrate it with respect to the current predictive distribution. So we're assuming that the materialized value here, y prime, has the current predictive distribution as an underlying distribution, and then we get criterion which is just depending on the predictive distribution. It's very straightforward to show that this expression can be simplified to the one on the right, where you just have the CDF times 1 minus the CDF, again integrated with respect to the weighting measure. If we are coming back to the scenario we were targeting, so where we have a Gaussian predictive and first this indicator weight, then it's very nice that we can find an analytical formula of how this expected threshold-weighted CRPS looks like. Similar for the second weighting measure, even if the expression looks very, very different. So it's super nice that we now have these analytical expressions, and we can basically now take them to our test case. So you remember that we had this photo switch data set with currently 100 molecules to train, and now we want to select the 101st molecule. So you have all these 300 candidate molecules in blue, and on the right you can see the corresponding values of the expected threshold-weighted CRPS with the new one. And what we now would do is that we would add the molecule which currently has the highest value, which is the one you can see indicated with the blue cross. It's one which has a very high prediction, which is very different to the same figure if we are considering the new 2, which puts more weight around the threshold. So there, intuitively makes sense. We are selecting something which is closer to the threshold. Okay, so far so good. So now we are theoretically able to do targeted sequential design using this threshold-weighted CRPS. So we did earn a little break, and we're going to do a little sports break. Given that we are already in Cambridge, and you might think Scotland is not that far away anymore, why not trying out Scottish Highland Games? So you did find an event which is happening on Saturday, in which you would have to compete in these 6 disciplines. So there are 4 first disciplines in which you have to generally throw something very heavy, either very high or very far. And then there is also pole climbing and hill race. In case you cannot identify yourself with this guy here, I think everyone can do this. And just imagining you are now in this situation, you might have the problem that already in school you've always been very, very, very bad at pole climbing. But your second problem is that you're also not very good at throwing heavy things. So maybe you should select another discipline of sports, but if you really want to do it, you could ask yourself, now you have 2 days left, what should you train? So with the strategies we discussed so far, you would pick pole climbing, because pole climbing is the discipline in which you are the worst at the moment, right? It's the marginal distribution. But you might agree with me that given this setting here, it might make more sense to actually train to throw heavy things, because then in total, you will be better in the end. And that's the other kind of sequential strategy you can use, which is also known as stepwise uncertainty reduction. So these are strategies where you are considering the uncertainty over the entire domain. And we can, of course, also make that a lot more mathy. So given that we have a Gaussian process model Xn currently at time n, we want to select the next acquisition point by minimizing this function. So in this function, we have 3 things which we have to explain. So the first one is Xn plus 1. Xn plus 1 would be the future Gaussian process conditioned on the observation event if we add this observation. Then we have the functional H, which is an uncertainty functional mapping the whole updated GP to a value, whatever that might be. And the third thing is this expected value, which denotes the conditional expectation with respect to the current GP. And we need this, again, because we cannot evaluate all the potential values we want to add. So we do have to work with an expected value. In the realm of the threshold-weighted CRPS, what we are using is the expected value of the integrated CRPS. So we would have the point-wise threshold-weighted CRPS, and then we are just using the integral of that, so basically the threshold-weighted CRPS of all the molecules in the molecule scenario. If we swap here the expected value and the integral, we get this like inner expression which has a fixed x and a fixed x prime. And using this and the Gaussian assumptions and our weighting measures, we again get some pretty nice expressions which we can then use in the sequential acquisition strategies. If we do this, we get very similar pictures as before. So first, now we have the integrated threshold-weighted CRPS nu1. We would again select the molecule which has a very high, which is very much on the right. And for the nu2, we would again select something which is way much closer to the threshold. Okay, given that we now have our 4 sequential data acquisition strategies, we can now try and compare them. How do they work? What are their advantages? What are their disadvantages? For this, we are slightly changing our scenario. So we have the same data set as before, but what we are doing now first is that we are isolating 100 validation molecules. We are doing this to ensure that until the end of the data acquisition, we do still have molecules which are in the range of interest. We don't want to add all the interesting molecules. Then instead of starting, the validation molecules are the pink dots, and what I'm showing here is the predictive mean at the moment. And now I'm not starting with 100 initial training molecules, but I'm starting with 30, which you can again see as the red crosses. And the candidate molecules are again represented by these blue bars. Now it's just 260 left as we excluded 100. What I'm doing now is I'm adding step by step 1 molecule for like 50 iterations using the pointwise, so not the integrated threshold-weighted CRPS nu1. So you still see the criterion on the right and on the left, how the molecules are added and how the Gaussian process for the candidates, but also for the validation molecules is evolving. You can see that using this criterion, we're still adding a lot of molecules which have high predictive and also high true responses. And if you now compare the final image with the first one, you hopefully can see that the predictions, especially within the excursion set of the pink dots, are a lot better. We can do exactly the same video using the other criteria, and we will observe actually slightly different things. And that's also something which you can now see on this plot. So what I did here is that I did 60 repetitions, always using different validation molecules and different initial training sets. And I then ran a random acquisition strategy, so one where you just randomly added molecules, and the 4 criteria we were using. On the left, you see the threshold-weighted CRPS as evaluation measure, because it's still an evaluation measure. That's what it was supposed to be originally. And you can see, not very surprisingly, the criteria which focus on nu1 perform better in nu1, and the nu2 perform better in nu2. What we also observe is that for nu2, the stepwise uncertainty reduction one performs clearly better, while for nu1 they are very similar. We would maybe expect that the integrated one performs better because that's actually more targeting what in the evaluation is eventually shown. What I'm also showing is that if we apply some classification on the final GP, just using the predictive mean to build a classifier on, we can observe those 2 dynamics here. You do very clearly see that the nu1 strategies perform a lot better in precision, while the nu2 strategies perform a lot better in sensitivity. what again intuitively makes kind of sense, because once we explore around the threshold and once we really explore the excursion set. Okay, so this much about chemistry. I will use my remaining 5 minutes to very, very briefly talk about the second application we have, so the agriculture one. That's very much ongoing work, so it's not final results. It's really just to show that those strategies are useful in a wide range of domains. So, as I already said at the beginning, in the agricultural application, we are interested in, they call it in the agricultural literature, G times E prediction. So it's genotype times environment. So it's which genotype or which variety performs well in which environment. For this, we now have to account for the fact that our input space is a genotype and an environment. And in the data set I had, the genotypes were characterized by SNPs, which is basically genetic data, which is strings. And the environments were characterized by their meteorological conditions given by time series. So there we had things like solar radiation, temperature, precipitation. To use this in a Gaussian process model, what we now had to do, or were doing, is that we were using kernels on the genotypes, so kernels on the strings, and we were using kernels on the time series, and then we combined the kernels into the combined kernel space, and then used that to do the GP model. What kernels you can use for what would be the content of another talk. For the moment, I'm just assuming that that worked more or less good. Okay. If we now do that and have a model, we can now again ask ourselves how or in what setting data acquisition would be useful. And so the data set we are using is a novel data set, which is about wheat, so not wheat, but wheat performance, and it's about yield and protein content, and it was collected in Switzerland. And so what our collaborators from Agroscope told us is that what they're very interested in is to predict for new varieties. So assuming you have some new varieties which come from abroad, you want to predict in which environments these varieties would perform good. So what I did here as a rather simplistic first test is that I isolated 5 varieties from the test set, and then I just started with 100 random training points from my data set, and then I added 5 times 3 new measurements. I did that in a very brute force and not in a very elegant batch sequential strategy. But what you can already see in this very easy or simple test is that I'm showing here sensitivity, assuming that we are still targeting combinations which lead to performance evaluations which are above a certain threshold. So we want to have protein which is higher than x epsilon. And you can see that compared to the random approach, where after adding 5 times the 30 new observations, we would have a sensitivity of 40%, and here using just the pointwise CRPS nu2, because it's very ongoing work, we already had 60%. What would that mean? So this here is the average over 10 repetitions only. If we have a look at 1 repetition, yeah, I think the state of it's as ongoing as the figures are not very sharp. So you do see the true value and the predicted value, so you want to have values on the diagonal. And you can see that with the random approach, so with the crosses, you would detect a lot less combinations of these new varieties and environments, which will lead to nice outcomes. So given that we use some clever targeted design and strategy, here at the end of the day, we could really kind of say that, okay, those new varieties perform well in this set of environments. Good, so I'm coming to the conclusion. So we did introduce 4 new pointwise and integrated CRPS-based criteria for targeted sequential design. They did show promising performances in both molecular and agricultural test cases. And as I said, the agricultural test case is very much ongoing work. There would be a lot of other domains in which we can also do very similar things, which would hopefully be helpful. And of course, we could consider using different weighting measures with the CRPS, but also generally kind of expanding this whole sequential design using scoring rules scenario. The two papers, or the two manuscripts this talk is based about, are now available on arXiv. Here also, again, you see a list of all the authors I was working with. And with that, I'm going to finish, and I'm very happy to answer any questions.
Thank you for your talk. Any questions?
Thank you for the talk. It was great. In the case of the integrated CRPS criterion, as you're doing sequential design, did you encounter this problem we have also for other simpler criteria like expected information gain? The fact that you do not approximate well your expectation. I mean, for sequential design,
Yes.
So there is two things. I mean,
Yeah.
It's in principle it's better to do integrated, but the approximation of your expectation is not that good. Or
Yes.
can you elaborate on that?
I mean, in general, as we are assuming that the materialized value has the current predictive distribution, we're always just as good as our current predictive distribution, in a sense.
Yeah.
So, I mean, if our current predictive distribution is flat,
Yeah.
we will not get anything useful.
Mm-hmm.
For how that compares in the pointwise versus integrated case, I'm actually not sure. I guess it also depends on if you are really like partwise very good or bad, or if you're generally very good or bad. I would assume that yes, if your model is good in certain parts but very bad in others, then I guess the pointwise would still, but at the same time it would lead you to a certain region of the space and you would not explore the rest. So you might actually also want I mean, if you do the integrated, it would also send you to the regions in which your uncertainty is very high, even though you have no idea if you're close to the threshold. So I guess it would still make sense to at least use maybe a I mean, at the end of the day, you could also use a combination or some kind.
Other questions? So I have a question. So sequential decision making is great, and I have a question. In your approach, did you integrate the trade-off between accuracy and the cost? Because data acquisition, maybe it costs something. Are you going to take new molecules infinitely if you can? Or if your model is already accurate enough, are you going to stop at some point?
We didn't consider that at all until now, because we were always a bit like, so we had one project in the chemistry context where they really told us, we are doing this new lab experiment in 2 weeks, we need 48 molecules. And so I think we basically did begin doing this also in different contexts than I've just been talking about today, but it would certainly be a very important factor to come up with a stopping criteria, or at which point does it still make sense to add molecules and when not.
And I have the question, so when you take a new molecule, do you update your model? Is it computationally heavy or is it very fast?
I mean, luckily within the whole Kriging literature, you have a lot of you have a lot of those iterative updating formulas. So just updating the Kriging formulas is rather quick, I would say, if you use this iterative structure.
Okay. Thank you. Questions? So then we thank our speaker and